Hello, welcome friends. This is Nashin Taj from the Department of Computer Science, SIT, Tumkur. Here I am presenting a lecture on implementation strategies of computer graphics. Looking at the definition of implementation, we can consider implementation process as a black box whose inputs are set of vertices and set of primitives. Hence, any implementation program must at least contain two loops that iterate over these sets. There are two basic strategies for implementation. One is image oriented approach, another is the object oriented approach. Object oriented approach. Here in this approach, the outer loop is over the objects. That is, for each object, we need to render the object independently. With the past old memory devices, there are two major limitations with this approach. That is the large amount of memory requirement and the high cost of processing each object independently. But with today's new memory device, these are not the existing limitations. And then the main limitation is they cannot handle most global calculations like shading effects and hidden surface removal. Image oriented approach has loops over pixels or rows of pixels called scan lines. That is, for each pixel you need to calculate and assign a color to that pixel. Here we work in the backward fashion to determine which geometric primitives can contribute to the color of a pixel. The advantages of this approach are we need only limited display memory at any time. The refresh rate is also high and the order for refreshing is simple, that is scan line by scan line. The main disadvantage of this approach is that unless we first build a data structure from the geometric data, we will not know which primitive affects which pixel. Hence, to use this approach, first we need to identify a proper data structure for the geometric data of the application. There are four major tasks in the implementation. One is the modeling, then geometry processing, then rasterization, and finally we have fragment processing. We have already seen these four processes in depth in the second unit itself as the units of graphics pipeline architecture. So we will have a brief look on it. Modeling. The results of modeling process are the sets of vertices that specify a group of geometric objects supported by the rest of the system. The modeler may also perform other tasks like clipping. Geometry processing. The goals of the geometry processor are to determine which geometric objects can appear on the display and to assign shades or colors to the vertices of these objects. In order to do this, it has four processes. One is calculating the projection of the points, then we have to assemble the primitives, then we have clipping and the shading. Rasterization. A rasterizer generates fragments with a process called scan conversion or rasterization. The rasterizer starts with vertices in the normalized device coordinates but outputs the fragments whose locations are in units of display, nothing but the real window coordinates. Finally, fragment processing. A fragment processor processes the fragments generated by the rasterizer in order to perform the following operations called texturing, translucent effects, and anti-aliasing. Clipping. Clipping is one of the processes used in multiple units of graphics pipeline architecture. It's the process of deciding which primitives or parts of the primitives fit within the clipping or volume defined by the application program. So, the basic clipping goes with the line segments, and the primitives that fit within the specified view volume pass through the clipper and are called as accepted primitives. Primitives that cannot appear on the display are eliminated and are called rejected or culled primitives. The first algorithm to perform the line segment clipping is the Cohen-Sutherland line clipping algorithm. This tells how to clip lines to fit inside the windows. It is easy to tell whether the whole line falls within the window or not, but with this it is harder to tell what part falls inside. Considering a straight line whose endpoints are P0 and P1 with a window whose bounds are WT, WB, WL and WR, which are nothing but the top, bottom, left and right bounds of the window respectively. So, the basic idea of this Cohen-Sutherland line clipping algorithm is first we do an easy test to find whether the line is completely inside or outside the box. If it is not, then we need a more complex test, and again we have to configure out how line intersects the box. To perform the trivial accept and reject test, these are the following steps. First, we have to assign each endpoint allocation code. Then we need to perform bitwise logical operations on the line's location codes. Then we accept or reject based on the result. The easy test has computation of a 4-bit code called the location code for each endpoint of the line. Basically, you can see on the window on the figure that the region surrounded by the window is completely divided into 9 regions, and each region will have a unique 4-bit code. To calculate the 4-bit code of the endpoint, we go with the x and y coordinates of each endpoint. The bit 1 and bit 2 of location code is related to the y coordinate of the endpoint, and bit 3 and bit 4 to the x coordinate. Whenever the y coordinate of the endpoint is greater than the top bound of the window, then bit 1 is set to 1. When the y coordinate is less than the bottom bound of the window, then bit 2 is set to 1. If the x coordinate of the endpoint is greater than the right bound of the window, then B3 will be set to 1. Else, when the x coordinate of the endpoint is less than the left bound, then bit 4 is set to 1. So after we calculate the location code of each of the endpoint, we need to perform the logical operations onto it, bitwise logical operations, to find whether the line is completely visible. We apply the logical OR operation on the location codes. The line would be completely visible or inside the window if and only if when both code values of the endpoints are 0, or else the logical OR operation on it on the location codes is 0. If the line segments are completely outside the window, then doing a logical AND operation on the location codes will be a non-zero value. Then the third case would be we need to clip the line to have the partial display of the line. In this case, we would do a bit flip. For example, if we consider that the bit 4 of the location code is set to 1, then we need to flip the x coordinate of that particular endpoint, for example x0, with a new x value that would be equal to the left bound of the window, and then we need to find exactly the point of intersection, that is xc comma yc, with the window. To find the point of intersection, we can easily and clearly see that xc is nothing but the left bound of the window, and then using the similar triangles visible in the figure, you can solve the yc as the left bound of the window minus x0 divided by x1 minus x0 into y1 minus y0 plus y0. Once you have computed the point of intersection, then we replace the point of intersection with the end point lying outside the window. Again, recompute the code and continue until all bit flips are processed. In the similar fashion, we check with the other bits. It could be B2, B3 or B4, whichever bit is set to 1, we need to flip that bit with the bound of the window and then recompute the point of intersection with the window, and again compute the location code for that point of intersection and find whether the logical OR operation on the location codes of the endpoints is resulting in 0. So this is the third case where the two endpoints are outside the window, but the middle part of the line is visible as it is lying inside the window. The second algorithm for line segment clipping is the Barsky clipping algorithm. Depending on the way we express the line segments, we can use different approaches for line segment clipping. Suppose we have the endpoints as P1 and P2, and we take the parametric form of definition for a line. We get two scalar equations. Those are x alpha is equal to 1 minus alpha x1 plus alpha x2. Similarly, y alpha is equal to 1 minus alpha y1 plus alpha y2, where alpha varies from 0 to 1. Whenever alpha value is negative, we can move to other side of the P1, and when alpha is greater than 1, then we move to the other side of P2. Looking at the figure, you can see that we can obtain 4 alpha values for finding whether the line is lying inside or outside a given window. The 4 alpha values are respectively with the 4 bounds of the window. Alpha 1 corresponds to the bottom bound, then alpha 2 is with the left bound, alpha 3 with the top bound, and alpha 4 with the right bound of the window. So once we calculate all these 4 alpha values, we need to analyze the order of parameters. If the order is in the first form, that is where 1 is greater than the alpha 4 and then alpha 4 greater than alpha 3 is greater than alpha 2 and alpha 1 is greater than the 0, then the line segment has to be clipped. Else, if the order is something else, it could be like 1 is greater than alpha 4, then comes alpha 2, and then there is alpha 3, and then it is alpha 1. Hence, the line segment would be rejected. Here there are only 2 cases. One case is where we have the series that alpha 4 to alpha 1 greater than the zeros and less than the 1. Another case, it could be some other order of alpha values where the line has to be completely removed. So hence this algorithm minimizes the number of intersections to be calculated, and the advantages are it can be easily extended to 3 dimension using values of alpha. We do not have to use algorithm recursively as with Cohen-Sutherland algorithm. Barsky clipping algorithm in 3 dimension. In order to extend this in the 3 dimension, we need only to add one more equation to the scalar representation of the line. That is z alpha is equal to 1 minus alpha z1 plus alpha z2. The major differences between 2D and 3D clipping is, in 2D we will clip line segment against line of a window, but in 3D we will clip the line segment against plane of a window. The point of intersection can be calculated by using this formula, where n is the normal and p naught is a point on the plane. Clipping in 3D with Cohen-Sutherland algorithm could be little bit complex, as the region across the 3-dimensional window is divided into the 27 regions. Hence, there would be more outcodes for Cohen-Sutherland algorithm, and it would be little complex to find the partial part visible inside the window. Hence, line or plane intersection test in Barsky is easier than Cohen-Sutherland line clipping algorithm. Coming to polygon clipping, we can consider a polygon a two-dimensional object with an interior. Polygon clipping is not as simple as line segment clipping because clipping a line segment yields at most only one line segment, but clipping a polygon can yield multiple polygons as shown in this figure. However, clipping a convex polygon can yield at most one other polygon. Hence, whenever there is an application to deal with the concave polygons, we need to try to convert those to convex polygons. One strategy is to replace the non-convex polygons with a set of triangular polygons, and this process is also called as tessellation. Line segment clipper can be considered as a black box, and in order to clip a polygon, we can clip with respect to each bound or each side of the window. This black box again has inputs nothing but the four endpoints of the window and also the two endpoints of the line segment. Clipping line segment against top side of the window has the inputs the two endpoints and the y max value, and then clipping against each side of the window is independent of other sides. So you can see that we can clip the polygon with respect to every side of the window independently, and hence we can use four independent clippers called the top, bottom, right and left clipper. Then we can have a pipeline clipping of polygon in the fashion as shown in this figure. To extend this for 3 dimensions, we add front and back clippers. Clipping of other primitives can be done with other approaches like bounding boxes. Rather than doing clipping on a complex polygon, we can use an axis aligned bounding box or extent. Smallest rectangle that is aligned with axis that encloses the polygon is called as the bounding box or the extent. It is very simple. We need to compute the maximum and minimum of x and y values and then find the surrounding bounding box for the polygon as shown in the figure. Then you can usually determine accept or reject based on only bounding box, but in order to find the partial visible part of the polygon, it requires again a detailed clipping process. The curves, surfaces and text can be clipped out with different approaches. For simple curves, we can find intersection points and perform clipping similar to line segments. For complex curves, finding how many number of intersections to be calculated is also difficult. So, complex curves need to be approximated as line segments and surfaces for clipping. For clipping, text need to represent it either as bit pattern or as any other geometric object. Clipping can be done in frame buffer through a technique called scissoring. So here we stop our lecture. Then we see the rasterization part in the next lecture.